Hello everyone, I'm Zhao Jing from Department of Electronic Engineering in Tsinghua University. Our paper talks about language recognition based on unsupervised pre-trained models. The presentation includes introduction, related works, method, experiments and results, and conclusion. Language recognition is a task to find out what natural language is being spoken. It's usually a multitask classification problem. The figure shows the general technical process of the language recognition system based on neural networks. So the feature of embedding extraction is an important part. Language identity is discriminated by the way phonemes are arranged. We need to extract proper representations with long-term information. The pre-trained models are responsible to output general features with enough context information. This is our starting point. Language recognition is not a new research topic. There are many traditional methods to LRE. The n-gram one is a classical way to judge a language identity. First, a phone recognizer is needed to provide phone label for a given speech segment. Then we can build n-gram phone models with the phone sequences. Finally, support vector machine makes the decision. This performance is affected by the phone recognizer accuracy. The X-vector is a popular method to speech recognition as well as language recognition. It is based on two-part neural networks. The frame level and the segment level networks are connected by a statistic pooling layer. After obtaining the X-vectors, we can get the final results with PLDA, that is probabilistic linear discriminated analysis. This method usually performs better than the above one, but it still relies on large amounts of labeled data to obtain satisfactory results. We will pay attention to feature extraction-based methods. As mentioned above, the X-vector is a popular one. Besides, the multilingual botnet features and bot-like feature extractor are proposed as well. They are under full supervised condition, which may suffer performance degradation when labeled data is limited. For unsupervised learning methods, we still can extract general representations with limited labeled data, so we employ the recently proposed speech pre-training methods to the LRE system, such as CPC, APC, Wei-Qiang APC, and NPC. They are briefly introduced next. Contrastive predictive coding is a contrastive learning method. The encoder extracts the embeddings which are imported to the context network. Then the network is optimized to discriminate the positive examples from the negative ones. Different from CPC, autoregressive predictive coding is a generative model. The objective is to predict the spectrum of a future frame. The L1 loss is usually used. Vector quantized APC is developed based on APC. An additional vector quantization layer is added to transfer the embeddings to discrete tokens. The method is validated to be effective with experiments. The last one, non-autoregressive predictive coding, is also a generative model, but it concentrates on mask reconstruction rather than predicting. Besides, the designed convolution block model can restrict the information forward process with receptive field. This makes sure that the construction relies only on local dependencies of speech. Now we have overviewed the four methods of unsupervised speech pretraining. We can contrast our system. The overall system architecture is as below. First, we train the self-supervised models with speech data only. Given a speech sequence, we put it to the pre-trained model to obtain latent embeddings. Then the downstream classifier is trained with the embedding and the corresponding labels. To obtain better results, we train different downstream classifier structures, such as linear classifier, multilayer perceptron, as well as recurrent neural network. For the experiments, we used two datasets for unsupervised pretraining, the English dataset LibreSpeech and a multilingual dataset CSS10. LibreSpeech is a dataset of reading English speech, and we only use the clean 100 hours and the 360 hours subset. The CSS10 dataset is a collection of 10 languages spoken by 10 speakers respectively. The total duration is about 140 hours. For LRE task, we use the dataset from Oriental Language Recognition 2020 Challenge, including AP16 and AP17 and AP20 OLR channel test. The first two subsets are putted together to get a collection of 10 languages spoken by over 200 speakers. The total duration is about 100 hours. The AP20 OLR channel test is a collection of 6 languages in different channels. The total duration is about 10 hours. Then I will introduce the experiment's results. For the first group experiments, we use 100-hour English speech data from LibreSpeech to pretrain. Then we randomly select 10% of the AP20 dataset as well as the supervised dataset. The rest 90% data are used for testing. To compare the influence brought by the amount of the data, we also repeated the experiments with AP16 and AP17. The results are shown in Table 2. The settings are the same as AP20. The system performance is evaluated with accuracy and C-average, which is a weighted sum of false alarm rate and miss rate. From the results, we can find that the pre-trained systems perform better than the traditional systems with two datasets. But different pre-training methods do not make big differences. And as for the classifiers, MLP and RNN get a little better results compared with linear ones. Comparing the two tables, we can find that the amount of labeled data as well as the number of languages do not influence the performance of the pre-trained models much. So the pre-training based methods are suitable choices for low resource conditions. The observations from this group experiments are listed here. We will not go through this. Then we changed the English dataset with the multilingual dataset CSS10 for speech pre-training. The supervised training still uses the AP16 and AP17. The results are presented in Table 3. The performances with the CPC model does not have much inferiority to models pre-trained on English datasets, so we can infer that representations are transferable across languages and the English dataset can provide enough information to the pre-trained model. For the last group experiments, we tried the domain mismatch test, that is AP16 and AP17 is used for training, and while AP20 is used for testing. The utterances of the latter are recorded with different channels. Since there are only 6 languages in AP20, we select the corresponding speech data of the 6 languages in AP16 and AP17. From the results in Table 4, we can see the performances decline apparently in cross-channel tests. MLP classifiers have lost the weaker advantages compared with linear ones. The results suggest that pretraining does not provide enough information to the cross-channel test. So we increase the amount of the pretraining data to 360 hours. The numbers in Table 5 shows that more pretraining data can improve the performances, which indicates that large amount of pretraining data is necessary to cooperate with domain mismatch problem. To better illustrate the working mechanism of unsupervised models-based system, we realize the representations learned by the self-supervised models with TSNE. Different colors stand for different languages. From the figures, we can find that the languages' identities are well separable, while the cluster status also suggests there are other irrelevant information, such as speaker, accent, and channel information. Finally, there are some conclusions of the strengths and weaknesses. For the strengths, representations are well separable. We can make use of unlabeled speech data while working well with limited amount of labeled data, and simple classifiers can obtain satisfactory performances as well. However, representations extracted may contain irrelevant information. Generality and robustness are restricted by the speech data used for pretraining. Last but not least, pretraining is costing. For the future work, we will enhance the robustness of unsupervised features, explore a broader range of applications, and design better classifier architectures to reduce the influence of speaker and channel information. That's all. Thank you for your attention.
For language identification task. So, any question for this paper? I have some question. The first, you in the conclusion, you said the pretraining is time using. How long you use to pretrain such as liquid speech 100 hours?
As for the pretraining, I didn't record the specific hours for training. I think for the 100 hours, train a pretraining model would cost 2 days or 3 days.
Okay, with how many GPU card?
Just one card for a model.
Okay, so you use the Web2Vec tools? Web2Vec tools?
No, for the pretrained models used in this paper, we just use some small models, APC, CPC, NPC, not Wave2Vector. That's too large.
So you use CPC with other tools, but Web2Vec now is it seems very popular for other tasks such as speech recognition and speaker recognition. So you can also try it.
Yes, we also tried the Wei-Qiang vector for other downstream tasks.
Okay, another question is the classifier. You use a simple classifier. Have you compared other classifiers such as LDA or PLDA for the language application?
Since the time is limited, we didn't perform much experiments with other classifiers, just the simple ones.
Okay, thank you. This is a very good beginning. I think the pre-trained or the unsupervised learning is will become more and more popular beside the language identification task. Other tasks also used. So I hope to see more works in the future. So is there other question? If you have question, you can also type the question in the chat box. I have a final question. In your presentation, include the paper, you say for the multi-channel, cross-channel, the pre-trained model seems had worse performance. So it's probably due to the pre-trained database. You use library speech, but it doesn't include many channels. It's like this question. This is a problem.
Yeah, we think the performance were worse because the pre-trained data is too clean, just one language and the data size is small, just 100 or 300 about. If you use more data and with more language, more languages would be better. But we didn't perform more experiments.
So in the future, you can try Giga speech or CNCLab, large database.
Yeah.
Okay. Maybe this will need very many GPU.
Yes, that's very costly.
Okay. So for the web topic, there are some pre-trained model based on more large database. Maybe we can use it directly.
Yes. That's a good way to. Yeah.
Okay. Thank you very much.
Thank you.
So